This is Electrostatics, Lecture 5. The early stuff we're going to do, we probably could have did at the beginning of the class. Usually the first lab we do is talking about different ways to move electrons and build up charge. And we didn't talk about it, so I know some of the questions on the long Kappa site have to do with conduction and induction, so there'll be a little demonstration on that. And then we're going to do parallel plates. So to start, right, building charge, there's a few different ways to build charge. We could build charge through batteries, which you might or might not have learned in chemistry with voltaic cells, which uses chemical reactions to move electrons around. Then there's static electricity, which is rubbing one thing against the other and removing it. You know, if you ever like rub the balloon in your hand or in your hair or on your clothes, right, then you are moving electrons from one to the other just by giving it energy. And then the third way that we're going to talk about, which won't be this lecture, is through the production of magnetic fields or using magnetic fields to move charges around, which will be generator reactions, which will be a big topic down the road. So we are going to look at what is conduction and what is induction first, and let's start there. Okay, one of the things we're going to look at is charging by conduction and induction. And those terms, conduction and induction, are going to come up probably more than once. So this is probably something we should have talked about at the very beginning of electrostatics, and we didn't. So I'm going to bring it up now. It is some of the questions on long Kappa. And like I said, these terms are terms that we probably should know. And this would have been a lab that we would have done to start electrostatics. And we didn't get a chance to do it. So what I have is I have an electroscope, which is just kind of a fancy term for two pieces of tinfoil hanging inside a flask. And I am going to build up charge on these a few different ways. I'm going to build up charge through conduction, and I'm going to build up charge through induction. So there's not too many things that we have to know to start this, but we will make one rule. We make one rule that when we take fur and we rub it on plastic, the plastic becomes negatively charged. So the process of rubbing these together, electrons leave the fur, they go into the plastic, and that plastic becomes negatively charged. So I can create negative charge. I can make this rod negatively charged, right? And I'll also say on a wet day like today, or wet days on pretty much any day in spring, this isn't the best time to run this experiment, which is why we normally run it in March or even in the winter when it's dry and cold, which you know, if you ever had staticky hair or something like that, usually it's on those cold, in the winters when this happens much more. In the summer, not so much. In wet, rainy days like today, again, not so much. So this isn't going to have the dramatic effect that we could have at another time, but it works. Okay, so first thing I'm going to do is I'm going to build up a charge on this rod. So I do that, and now through conduction, I will charge the electroscope. So we could see already that these two pieces of tinfoil are separated. I'm going to do it a few times, try and get some charge on there. And we can see right now it's charged, right? And I know it's charged because even though it's not as drastic as other times, right, these two pieces of tinfoil are repelling each other. Let me put my finger on it, get rid of the charge. Now they're back together. Now there's only two things that this electroscope can tell me. It can tell me that the pieces are not charged, or it can tell me the pieces are charged. I can't tell by looking at it if it's positively charged or negatively charged, right? And it's impossible for one to be charged negative and one to be charged positive, because if that was the case, the charge would simply move over to the other side, right? If one piece of tinfoil had an excess of electrons, the other one had a shortage, well, then some of the excess would move over to the other side, right? So these two pieces of tinfoil can only be charged the same way if they're charged. Right now, they're not charged at all. They're just hanging straight down because of gravity. Again, I'll charge it up. I want to kind of get it off there. There we go. And I'll add a little more charge. So there we go. So now I know these are charged. And these are charged through conduction because you saw that I was taking the rod and I was touching it to the electroscope. So this is charged negatively. And I know it's charged negatively because I'm going to test it in a second. But I have an excess of electrons on this stick. I touch it to this, which creates a path for some of the electrons to leave and go to the electroscope. And again, on a wet day like this, we start to lose charge into the air kind of fast. So I'm going to charge it up again. But we can see it's charged. They're not as great as before. We can see it's charged. Now, I also know it's charged because if I bring this near it, they start to separate more, right? So I'm not charging this by induction or conduction right now. I'm just simply looking at the electroscope. And I know it's charged slightly. I also know it's negatively charged. When I bring a negative rod near it, it makes them spread apart more. Now, why is that? So there's an excess of electrons in this electroscope. I bring something negative towards it. That takes the electrons that are on the top, the excess ones, and it pushes them down. So now the leaves spread out more when I bring it near it. Right? Let's charge it a little more. But just then, I wasn't really charging it. I was just testing it. I was simply moving the charges around. Right? So build it up a little more. And I can see it's negatively charged. When I bring the rod near it, it moves apart even more. All right, so now let's bring it to neutral. So conduction is really a fancy way of charging something through contact. Induction, we're going to see, is charging something without contact, and we're going to be able to induce. And induce is something, that's a word that means the same thing in a lot of different places, but it pops up in other places, right? So now we're going to use induction to build up a charge. Now, how I'm going to do that, I'm going to start out the same way. I'm going to charge up this rod. I'm going to hold it near it, except without touching the rod to anything. I'm going to touch the electroscope with my finger. I'm going to take my finger away. I'm going to take the rod away. Now I can see that it's charged again. Again, it loses charge kind of fast because it's not the day for this, but we could see that I charged it up. Now I charged it up through induction. I'm going to do it again. Right, and now it's charged. Now, the next thing we're going to do, and I'm going to do it kind of fast, is I'm going to charge it through induction, and then I'm going to bring the negative rod near it, and I'm going to see what effects it has on it. Now, if I bring the rod near it, and those leaves spread apart even more, electroscope must be negatively charged. If I bring the rod near it, and the leaves come together, then the electroscope must have been positively charged. Because if I bring the rod near it, and the leaves were positively charged, and it pushes some electrons down there, it makes it more neutral, which means the leaves would come together. So, let's charge it up. Touch it with my finger, take my finger away, it's charged. Now, every time I bring this near it, brings it closer together. So, when I charge it through induction, the electroscope became positively charged. When I charge it through conduction with a C, it became negatively charged because electrons simply left the rod and went into the electroscope, conduction. When I charge it through induction, the electroscope became positively charged. Why is that? Because I brought the negative near it. And now all the free electrons in the electroscope want to get away from this. There's nowhere for them to go right now, so nothing really happens. But if I touch it, that makes a path so the electrons can leave. A bunch of electrons leave, which means it now has a shortage of electrons. I take my finger away, then I take the rod away. It's now positively charged. So there is conduction and induction. Now, we'll see we can build up charges through various ways. We can build it up like we did, which is basically exciting something or add an energy to it to break electrons free and then move those electrons around, right? Which is static electricity. So we could build up charges through static electricity. We won't really be talking about what we could. Okay, so there's examples of conduction and induction. Conduction involves contact between the charge and body and whatever I'm trying to charge. Induction means that the charge and body, which was the rod in both cases, does not come in contact with the thing that I'm trying to charge. So, again, those are ways to build up charge. Second thing we're going to talk about in this video are parallel plates and what happens with parallel plates. So parallel plates, what are they? Excuse me. They are just what we're saying. They are two pieces of metal, or two metal plates that are running parallel to each other. And then we hook up a power supply to them, and what happens? So let's say I have these parallel plates, and I hook them up to a battery. Now, if I hook them up to the battery, let's say that this is the positive side of the battery, just the way I have it marked. This is the negative side of the battery. If this is the positive side of the battery, if there's any free electrons that it can pull off this plate, they are all going to leave because they're going to be attracted to the positive side of the battery. Negative side of the battery has excess of electrons, and they all are pushing away from each other, so a bunch of electrons will build up on this plate. So we will have a shortage of electrons up here, making it positively charged, and then there will be an excess of electrons down here, making this negatively charged. So that, in essence, is what a parallel plate is. We're going to see later that this is also what we call a capacitor, and there's different uses, but we are going to focus on what's going on here in between those two plates. So again, I want to kind of highlight a little bit of a lab that we would have done that we're not going to be able to do now. And this lab is going to involve checking voltages on different points. So what we have is we have this sheet of paper, and this sheet of paper has metal built into it here, and you can't see it, but you will. On the other side, there is metal on this side. So there is metal placed into the paper. This is hooked up to a power supply, making this positively charged. This is hooked up to the other side of the power supply, making this negatively charged, much like we're talking about there. I've essentially hooked it up to a battery, so one side is positive, one side is negative. So these aren't plates that have any depth to them, but it's still going to serve the same purpose. So all of this metal here all has a shortage of electrons, and over here, all of this metal that my hand is covered up at this moment has an excess of electrons. So we hook it up, we establish parallel plates, and then what I'm doing is I'm using a voltmeter. Now, a voltmeter measures voltage, right? It measures the change in potential energy per charge between 2 points. Oh, there we go. So now I am going to look at it and say right there, the better setup right there is actually my negative plate. So the voltmeter, with help from my daughter here, shows us that when I hook it up and it goes really high, well, then between the 2 points I'm comparing, there is a positive change in potential energy. And you can watch it goes negative like it just did now. There's a negative change in energy. But what I'm looking for is this one's not going to move, but I keep moving this one around, and I keep finding places where the voltage is zero, which means that the change in potential energy between one point and the other is zero, which means you don't have to do any work to get there. There's no changes in energy. And I'm finding all of these places. Now, this in the last one was the definition of equipotential line. So everywhere I find these points, and I'm finding them right here, 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 and I'm going to connect those dots in a second. Everywhere I find those points are lines of equal voltage. So this, and I'm going to draw it with the marker, but I'm going to draw it on the screen too. This is a line of equipotential because I kept one part of the meter here, I kept one part of the meter here, and I found other places where the voltage is zero. So all of this is the same voltage. I'm going to jump ahead a little bit here, if I can. Turn that off. And I did the same thing in the middle. So again, I have these points right there, right there, right there, right there. And again, notice I'm not moving the one over here, and I'm finding other places where the voltage is zero with respect to that point. So this is another line of equipotential. And then I'm going to do it one more time. And I could have done it other places, right? I could have put it here and found all places there. I can make as many lines as I want. I just pick one place with my left hand, and then I keep finding other places with my right hand and marking off those points. And as long as this one stays where it is, then everywhere else I find that has a voltage of zero on the meter, just trying to hold it still, but it's not always so easy. As long as the meter reads zero, then these are places where they are the same voltage, right? And I don't know what they are with respect to infinity, right? I don't know that, but I do know that they're the same voltage with respect to each other. So I'm starting to get points that are all, again, points of the same voltage as whatever the voltage is here. And therefore I'm making another line of equipotential. And we'll finish this one up. So my blue line is actually not as great as the real line was, because it should be more straight along. So let's pause that. And let's look at this. So I'm actually going to bring up this, and I'm going to erase all this stuff. Most of this is from my first attempt to make this video, my failed attempt to make this video. There we go. So we have these lines of equipotential, and so I have these lines of equipotential between the two plates. We are going to see these lines that run parallel to the plates that are lines of some constant voltage, right? So everything along this line here is all 1 voltage. Again, I don't know what it is with respect to infinity, but I know everywhere along this line it's the same. So if I had a positive charge right here, come on, if I had a positive charge right here, if I had a positive charge sitting right here, thank you, then it would get pushed away from this, it would get pulled towards this, and every time it crossed one of these lines, its potential energy per charge would change. But if I move this charge this way or this way along the line, it wouldn't take any work and its energy wouldn't change because everywhere along this line is 1 voltage, therefore 1 energy per charge. And if the charge doesn't change and the energy doesn't change, well then the energy per charge doesn't change. Now, these are equipotential lines, the ones in blue. And one of the things we know, and there's not that many rules between electric field lines and equipotential lines, but I do know that they strike each other perpendicular. So these orange lines are electric field lines. Well, that makes sense because if I had a positive charge here, which way would it get pushed? Well, it'd get pushed away from the positive and get pulled towards the negative. Now, I could take that even one step farther. If I had this charge sitting here, and I know this whole thing is all positive charges up top, there's a shortage of electrons everywhere on this, and the bottom is all negative, has an excess of electrons. Well, I know that the positive charges right here are pushing this down, and the negative charges down here are pulling this down. So for the charges directly above and directly below, there is a net force down. I know the charges over here are pulling down and to the right, but I know they're getting farther away from this, so their effect is less and less and less. So some of them are pulling to the right, but how much they're pulling gets less and less the farther we go. And these are pushing down and to the right, so same thing. These charges here and these charges up here are pulling down and to the left. These are pulling down and to the left. But again, as we get farther and farther away from this point, their effects are less and less because the distance is going up. So in the end, we could certainly argue that half of them are pulling down and to the left, half of them are pulling down and to the right. So the forces to the left and to the right essentially cancel each other out. So we have a net force, and that net force is straight down. So a charge right in the middle is going to get pulled right down, straight down. But the nice thing about this is this really holds true, right? If we look at our equipotential lines, then we know all the field lines run perfectly vertical. So that's telling us, hey, if I put a charge right here, come on, there we go. If I put a charge right here, and that's a positive charge, well, according to the equipotential lines, that's going to get pulled straight down also. And that's true. Now, we could argue, say, well, it's over near the end, so, these are pulling to the right, but there's a small amount pulling to the left, and that would be true. But there's a small amount pushing to the right, and there's a big amount pushing to the left. So really, in the end, it still all cancels each other out because we have all of this pushing this way, and we have a small amount pulling this way, but over here we have all of this pulling this way, and we have a small amount pushing this way. So the effects actually still cancel each other out. So the net electric field is still down, and over here we can make the same argument. Now, right on the edges, we could argue that these lines warp a little bit, because they're kind of out between the plates, which means that the field lines will warp. And this is all true statements. But really, between the two plates, there is a set electric field. And in my picture, that electric field is straight down regardless of where we are. So that's great. We have a uniform direction for this electric field. Well, the other thing that we could say is, and I'm just going to kind of say it without proving it mathematically, is when the charge is here, it's close to these positive charges, so the positive charges are pushing on this very hard, right? They're applying a large amount of force. These negative charges are farther away, so they're pulling, but they're not pulling as hard because their distance is more. As this charge moves, let's say we get to here, Well, these positive charges are pushing less because they're farther away, but it's getting closer to the negative charge, so the negative charges are pulling more. And as we move down, we can keep making this same argument. Well, that's useful because not only does the electric field have a set direction everywhere between the two plates, but the electric field has a set strength or set magnitude between these two plates. So all of that said, what we are saying is that when we are between these two plates, there is a uniform electric field, which means anywhere between these two plates, there is a constant direction of the electric field and there's a constant magnitude of the electric field. And this is extremely useful because we don't have to worry about distances, we don't have to worry about a lot of different things when we're talking about the electric field. If you put a charge between these two plates, we know where it's going to get pushed and how hard it's going to get pushed, right? And this is very different than any other situation so far. Now, that brings up a few different things. First of all, what's going to determine the strength of the electric field? What's going to make that electric field stronger, or what's going to make that electric field weaker? Well, one of the things that matters is how many charges we put on it. How many positive charges are here, how many negative charges are there. So the amount of charge on these plates is going to determine if it's a strong field or a weak field. And the other thing that's going to matter is how far apart these plates are. If these plates are very far apart, right, even if they're filled up with a lot of charge, if these plates are very far apart, well, you know what, the pushes and pulls aren't going to be so great because if these are real far away, they're not going to do that much. But if they're very close to each other, well, then they're both pushing and pulling. So, two things that affect the strength of the electric field. Now we'll go to the next one. It's the same picture. A lot of these are all basically the same picture, but it gives us an equation. So we know that there's a set electric field. It's showing some distortion on the ends, which we don't care about. As long as we're in between the two plates, the electric field is constant. But what's the electric field related to? Well, it's related to the distance. The greater the distance, the weaker the electric field. So it's an inverse relationship. But what determines how many charges we put on these plates? We're going to talk about these plates in more detail another time, but the most important thing is what determines how much energy there is the power supply we hook this up to. If we hook this up to, and this is a symbol for a battery, but we'll get into that more later. If we hook this up to a 9-volt battery, well, that means the battery is going to be able to do 9 joules of work per coulomb because it's going to change the potential energy by 9 joules per coulomb. So if we can do 9 joules of work, then every time it pulls an electron, every time it pushes an electron onto this side, it's capable of doing 9 joules of work per electron. So how much energy is it going to gain? It's going to gain 9 joules. It's going to pull electrons off, but as it pulls them off, they get harder and harder to pull off because this side attracts electrons. So how much work is it capable of doing while it's removing it? Well, it's capable of doing 9 joules of work for every coulomb of charge. So the voltage is telling us how much energy or how many charges it's capable of moving around. It's a very good measurement. Now, it doesn't give us the exact number of how many charges it puts on the plates, but to be honest with you, we don't even need to know that. If we just know the voltage, then these two things, there we go, these two things will get us the electric field. So we have a new equation for electric field. It's voltage divided by distance. Now, someone's going to use this equation incorrectly. And I want to explain something. This equation works for parallel plates, what we're talking about right now. It doesn't work for any other problem before this point, right? If I had a charge here and a charge here and I had a charge, and I didn't even have a charge here. I had a spot here, call it P, and I said, hey, what's the electric field at P? Well, this uses this equation. And this equation is when I have points of charge in different locations, right? So all of this goes together, but I can't use this equation for plates because plates are filled with charge. There's not charges in one point. There's charges spread out on this plate. There's charges spread out on this plate, right? And these plates are really 3 dimensions. These plates, are coming out of the board, out of the computer screen and into the computer screen, right? There's a length and a width to them. So this equation can't possibly work for this situation because there's no one place where I say, oh, the charge is right there. No, right? The charges are spread out all over these plates. So that's where this equation comes in. And then On the flip side, this equation, I can't use it for this stuff because it simply doesn't make sense. So I have to use the right equation for the right situation. This is the equation for electric field. Now, the other thing that we know is that what's voltage? Well, voltage, let's make this a little bigger. Voltage is the change in potential energy per charge, by definition, between 2 points. Well, I have 2 points. I have these 2 plates, right? Or I could pick another place. What if I had a charge here and I let it go to there, right? So I can pick points on these plates. But it's the change in potential energy per charge. So by our definition, we have this. So if I multiply it, if I move this around, I could say the voltage times the charge, which shows up a lot in problems on the website, must equal the change in potential energy, right? And if an object changes in potential energy, that could be how much work it did, right? But I don't love this equation because it could be anything there, right? It could be the change in potential energy, which means it could equal the work you had to do to get the charge there. If it's the other way around and I let something go and the potential energy went down, well, this change in potential energy could equal the kinetic energy that it gains, right? But either way, if I know the voltage, the change in potential energy per charge between 2 points that I care about, and I knew the charge, then I can figure out how much the potential energy changes. So if this is a 9-volt battery, if I moved a positive charge from here to there, it will have gained 9 joules of energy for every coulomb of charge that it has. All right, let's look at some examples. I'm going to start this one from scratch. So let's say we have a situation. We have 2 parallel plates. 1, 2, and I'm going to say this is positive. So I hook this side up to the positive side of the battery. And I'm going to say that this top one is negative because I hooked that side up to the negative side of the battery. And let's say I hooked it up to a 12-volt battery. All right, so I had a 12-volt battery sitting over here, and I wired it up. Oh, I'm going to need to change that, and we'll see why later. Negative, the shorter side always implies the negative side of the battery. The longer side always implies the positive side of the battery. So I hook it up like that. And I know that there's going to be a uniform electric field here. All right, so what else do I know? Well, I have these 2 plates, and I keep these plates, let's say, 20 centimeters or 0.2 meters apart. I keep hitting the button on this pencil thing. There we go, 0.2 meters apart. So first thing I can do is I can calculate the electric field between these 2 plates. It's going to be 12 volts divided by 0.2 meters. I want to say it's 60, but let's just check it real quick. 12 divided by that, 12 divided by 0.2, 60. So first of all, it works out to be 60 volts per meter, and that's good. Now, let's look at this, because once we know this, there's actually multiple ways we could use this information. Well, a volt is a joule per coulomb, and then there's a meter because it's volt per meter, right? Or I could argue that a volt or a joule is a kilogram meter squared per second squared. Joules will cancel out, one of the meters will cancel out. So I have a kilogram meter squared per second squared. Well, a kilogram meter squared per second squared is the same as a Newton. So I could certainly say, if I wanted to, that this is 60 newtons per coulomb, because I have newtons, which is all of this, and I still have a coulomb left here. So 60 newtons per coulomb, 60 volts per meter. They both are okay units for electric field. So I'm going to ask a question. I'm going to write both of these units over there because I was saying now this opens the door to solving things various ways. 60 newtons per coulomb, 60 volts per meter. I'm just going to put them to the side with the understanding now that either one of these units are fine because they both are measuring the same thing. But let's use this one. Let's use newtons per coulomb. That's a C. Let's actually write that neater. 60 newtons per coulomb. All right, and I'm going to ask a question. Let's say I have a proton, and this proton is sitting right up against this plate. And the charges in the plates really can't move, but I got this one in the air, and I'm holding it there. But when I let it go, I know it's going to go straight across, because that's where it's going to get pushed. So the question is, what is the maximum speed that this proton reaches? And we know as it's getting pushed up, there's a force pushing it up, so there's an acceleration up, so it's going to pick up speed, right? And we also know it's a uniform field, so it's a uniform force, so it's a uniform acceleration. Everything kind of works out nicely. Nothing's changing too much except for the speed. The speed's going up and up and up. So we're going to solve this with the concept of electric field first. It's going to take a decent amount of math and a decent number of steps, so kind of stick with me. And in order to do that, what am I going to do? I'm going to get rid of all this stuff. Get rid of all this. And we'll put some of it back, and I'll just kind of pretend, okay, this is my plates, right? And again, those plates were 0.2 meters across. All right, so here we go. So I'm saying it's a proton that I'm talking about, so I know it's going to get pushed up. Well, it is 60 newtons per coulomb. That's the field it's in. And I know the charge of a proton. And if I don't know, I could look it up, because protons have set charge, set mass, a lot of things, right? So I could do all this in one step, or I can consolidate the steps, but for right now I'm just going to break it up, right? So it's going to be 60 newtons per coulomb times 1.602 times 10 to the negative 19 coulombs. So that's the charge of a proton. There will be a force of 9.612 times 10 to the negative 18 newtons. That is how hard the proton will get pushed. Newton's law tells me the sum of the forces equals mass times acceleration. So therefore, the sum of the forces divided by mass equals acceleration. There's no other forces acting on this proton. Someone's going to say, well, what about gravity? Well, gravity is so small. This is a small number, but the force of gravity is so tiny it just won't matter, right? If we have a proton floating around in the air, then chances are the pull of the Earth is not the thing that's going to control what's happening to it. So 9.612 times 10 to the negative 18 newtons, and just to do it, a newton is the same as a kilogram meter per second squared, and we're going to divide by the mass of a proton, which, again, if we're not sure, we can just look it up. So what's the mass of a proton? The mass of a proton, hold on, I got my calculator, there we go. The mass of a proton is 1.6726 times 10 to the negative 27 kilograms. Kilograms are going to cancel out. I am going to have an acceleration. I'm going to have an acceleration of, I'm going to have to write, I'll write it here, 5.75 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 9th meters per second squared. So it's a small force, but it's a teeny tiny mass. Therefore, it produces a really big acceleration. So I know while it's traveling across, it's going to accelerate at this rate. Well, that's not the speed, that's the acceleration. But I have a displacement equation. And I know my initial velocity is 0. I know my acceleration. I know how far it's going to travel. It's going to travel 0.2 meters. So I can get the time multiplied by 2. 2 times the displacement divided by the acceleration will be t squared. So take the square root. That'll be t. So I'm not going to write it out because I'm running out of space, but I can plug these in. So it's going to be 2 times 0.2 divided by my acceleration. And then I'm going to take the square root of that answer. And how long is it going to take to travel across? 8.343 times 10 to the negative 1, 2, 3, 4, 5, 6, negative 6 seconds. So sure, it's a big acceleration, but it's over a really short amount of time. Then I know acceleration equals velocity final. So I'm using all these equations from chapter 1. Velocity final minus velocity initial over time. I know my time. I know my acceleration. I know this is 0. So velocity final equals acceleration times time. Well, I have my time. I have my acceleration. I can multiply those together, which I will, and it'll give me 47,944. So I'm going to do a little round, and I'm going to say it gives me 48,000 meters per second. There is my speed when it hits the other side of the plate. 48,000 meters per second. Now, we're going to look at the same problem. We're going to look at it differently. So I still have these two plates. There they are. Still positive. Still negative. Still 12 volts. Still 0.2 meters. And I'm asking the exact same question. But this time, instead of using newtons per coulomb, I'm going to use 60 volts per meter as the change in potential energy. So there is a change of 60 joules per coulomb, or 60 volts, for every meter that this charge travels. Well, it doesn't travel a meter. It travels 0.2 meters. So I take this. What do I get? Well, I get 12 volts. And I already knew this. I hooked this up to a 12-volt battery, so how much will it change from one side to the other side? Let me make one thing, make it exactly like the other one. This side was positive, right? It's not going to change any of my math, but this side was negative, and the charge is going to move up, and the electric field is up. So I can take the 60 volts per meter and multiply it by the meters that the charge is going to travel. I get 12 volts, which is good, because what did I hook it up to? I hooked it up to a 12-volt battery. So 12 volts makes sense. If I hooked up to a 12-volt battery, then go from here to here is a change of 12 joules per coulomb. Well, it is 12 joules per coulomb, and I know the charge of a proton, and it's still 1.602 times 10 to the negative 19 coulombs. So how much will the potential energy change? Well, it'll change by 12 times 1.602 times 10 to the negative 19. There'll be a change of potential energy of 1.9224 times 10 to the negative 18 joules. So that'll be the change in potential energy. Well, if I think about it, here's where it's going to have the most potential energy. Here's where it's going to have the least. So this will be potential energy lost. It'll also be kinetic energy gained. Two times kinetic energy divided by mass. Mass still plays into this, right? Everything still plays into it, just a slightly different way. That would be v squared. So I take the square root of it. That'll be v. So what do I have? Well, I have 2 times that kinetic energy, 1.9224. I'm going to divide that by the mass, which was, let's go back and look at it, 1.6726 times 10 to the negative 27. So I'm just looking at that screen to get the number again. I get all of that. I'm going to take the square root. And what does it work out to be? Well, guess what it works out to be? Works out to be the exact same speed. So I can look at this in terms of the change in energy. I could also look at this in terms of the forces and acceleration. Both of them get me to the same place. Now, I'm going to look at one more thing with this problem. Let's get a new slide down. And let's stick with this idea of $12 volts per meter. And I know, again, it's 12 volts per meter, and I know it's only 2 meters, so the math tells me between this point and this point there is a change of 12 joules per coulomb, right? So this is 12 volts. This is when it has a positive, this is when a positive charge will have 12 joules of potential energy per charge. Or if I move from here to there, this is when the potential energy will be 0. This is when I'll have 12 joules per coulomb. Well, what if I didn't release the charge right from this plate, right? This is the positive plate. This is the negative plate. So we're going to say this is 0 volts. If I put the proton right here, it's not going anywhere. It's already just going to go. It's just going to go right into the plate, or it's going to lean against the plate, but it's not going to pick up speed because it's already at the end point. So what if I started it? What if I started it here? And let's say that that was, well, this whole thing is 20 centimeters. So let's say it's 3 centimeters there, or 0.03 meters. Well, it's 12 volts per meter, actually. Let's write this better. 12 volts per meter. We're going to times it by 0.03 meters. It's going to be 0.36 volts. So this line of equipotential is 0.36 volts. Let's say, oh, sorry. Scratch that. I apologize. I knew that number didn't look right. Forget. The idea is right. Let's get the right numbers. So the electric field was not 12 volts per meter. It was 60 volts per meter. Sorry, let's rethink this. And I still want to know, this is 12, this is 0, which all makes sense because 0.2 times 60 is 12. Now, what's the voltage if we're here? Oof, that's a horrible line, but which is 0.03. Imagine that's a really good horizontal line. Now we're going to do the same thing the right way. Well, we did it the right way last time, just with the wrong numbers. 0.03 meters. Now we got something. This is a line that's 1.8 volts. If I want to do it halfway across, it's going to give me some type of crazy cosmic line. So then it would be 60 volts per meter. And we'll say it's 0.1 meters. Well, that's going to be 6 volts. So this line is going to be 6 volts. I'm not really drawing them to scale. Let's say that this last one here is 1.5 meters, or 0.15. 60 times 0.15 works out to be 9 volts. Right here would be 9 volts. And I know I'm kind of drawing things and fixing them, but where would 0.03 be? Well, 0.03 would be much closer. It'd be like right there if I wanted to draw better to scale, right? So 1.8 would be somewhere up here, right? So my point is, these lines that we set initially, lines of equipotential that run parallel to the plates, right? Or we found them with doing this lab. We can figure out what those voltages actually are, right? Because if I know the electric field in volts per meter, well, then I could just pick distances from the negative plate, multiply that distance by the electric field, and I can get what those lines are. Now, I can do the same thing I did here. I say, okay, well, if I didn't start from here, let's say I started from this point. Let's say I started it from 0.3 meters away. Well, if I started from 0.3 meters away, then I know it will have 1.8 joules of potential energy per coulomb. So I can do all the same math that I did here, except now it won't be 12 volts, it'll be whatever voltage I get, right? So for 0.3, it'd be 1.8 joules. I could do the same thing. If it was halfway across, it'd be 6 joules per coulomb, right? But I could pick those places because those lines will now have set voltages with respect to the negative plate, right? Because it's always a comparison between those 2 points. And with respect to the negative plate is really good because if I let a positive charge go, where is it going to stop? It's going to stop when it hits the negative plate. Okay, that is lecture 5. I'm not saying I won't do any more lectures, but it won't involve new material. It will involve, if I make any,
doing problems using what we've already discussed in these 5 lectures.